All right, everybody, welcome back. As I mentioned in yesterday's email, I'm going to take a bit of a break from the thermodynamics to cover organic structures and nomenclature. And that's what we're going to be doing for today and Monday. And it's because you have a worksheet that is going to happen next week. So if you're taking Chem 101, that's going to end up being an assignment. If you're taking Chem 121, it is going to end up being a laboratory experiment. That's what it is going to count as. So everyone is going to be doing that. That worksheet is going to be handed out on Monday for everybody's benefit. But I did promise you last day that we were going to do a demo that at least I think is really neat and interesting, and we're going to go do that right now. So this device started out as a YouTube video I saw, and the device was actually just the top half of this, and it ended up being what's called a hybrid rocket. It is a solid gaseous rocket engine. This cylinder in the middle is actually the fuel. It's acrylic plastic, and it is fed by oxygen. And when I talked to the gentleman out of the UK that actually started this, I asked him, it's like, have you thought about putting it on wheels and seeing if it will actually move itself? And he's like, no, I never thought about it. So ultimately, I ended up doing that, and it actually works. So we're able to convert energy into work. It takes a little bit to get it started, so with luck, this is going to work. Oh, that's hot. Well, it takes a little bit to get it started. The other side. I think that's going to work. Maybe go a little bit further in. There it's going to go. All right, get our stuff out of the way. And what you can see is that it's starting to light up the chamber just at a low oxygen flow. And it is burning its way through the chamber, so I'm going to take out the support. Like that. And when I put more now it's warmed up, let's see what it can do. Believe it or not, that was the oxygen cylinder on this end coming off. My oxygen tubing came off. So let's try that one more time. Take two, exactly. Oops. Low flow oxygen. Doesn't like that at all. Oh, started. Yeah. All right, so let's go for full power. There we go. There we go. Does security want to come in and see what I'm doing with your oxygen? She just walked past. Come on back here. I just saw that. So, just for the fun of it, I'm going to move back. And so one more time, just for the fun of it, as I increase the oxygen flow. Chemistry at work, yes. do I qualify as an engineer now? I get my degree?
Yes, 100%.
Anyways, thank you very much for the use of the oxygen.
Yeah.
Finally, we got an oxygen cylinder that has stuff in it.
There was weight to that one.
Yes, exactly.
Remember I told you? I knew there was one, but I sent an email. So
all of yours are empty. Yeah, exactly. All right, even the ones that are sitting in the full category are empty. I got to get back to class, so.
Okay, see ya.
Thank you, Beth. Much appreciated. And you shut that thing off? With regards to the comments, wish I was in class right now. Yeah, it is actually a really, really fun demonstration to watch. As you know, for me, as I was doing this and I put this thing together, kind of hoping it was actually going to work, and it did. And I'm like, woohoo, engineering, I can do this. So yeah, so we had a lot of fun with this and demonstrating it for schools and that type of idea. It's a really cool demo. All right, so that was one of the things I wanted to do. I wanted to provide you with that expression where we're now turning heat energy into usable work in the sense that it moves this rocket across the bench. Not enough to go up into space, but it's a starting point and it illustrates many useful purposes that we're covering in thermochemistry and thermodynamics. Where does one buy an oxygen engine? I had to get that one made, so you need an engineering. If you have someone who's got an engineering shop, it's actually pretty easy. The plans are pretty simple. I'll give you the plans. The other thing that I wanted to discuss was this. As part of the additional assignment for the solubility of salts experiment, there was I added the section that made it thermodynamics, that looked at the thermodynamic aspect of the experiment. And so this was what was missing and what I added. This is the equation that we need to use. And so that equation was, not in that color, natural log of the equilibrium constant K is minus delta H over RT plus delta S over R. And so when you plot natural log of K versus 1 over the temperature, what you get as a slope is negative delta H over R, and your intercept is delta S over R. So plotting natural log of K versus 1 over T gives you slope and intercept from which you can calculate the enthalpy of solution, solubility, and the entropy of solution here. So. What are the units? The units you get from the value of R. So when you multiply by R, you want units of energy in delta H and delta S. So the standard unit of enthalpy is generally kilojoules per mole, and the standard unit of entropy is joules per mole Kelvin. So that's what your units should come back with. Good. And that concludes, well, finishes off the thermodynamics component so that we can now look at organic chemistry. And what I want to do here in the context of organic chemistry is tell you that we're going to go through a number of PowerPoint slides and do a lot of examples on both structures and nomenclature. And then there's going to be a worksheet that you're going to complete next week. So the topics that we're going to cover is how to draw chemical structures, looking at the nomenclature of hydrocarbons, look at different functional groups, and look at functional group nomenclature. So this is material that should have been introduced in Chem 11. And we're just going to take it and build upon it. I do understand that for some students it is new. I am going to go through it, at least the first one or two examples, a little bit more detail, just to bring you up to speed on this material. But what I do want to do is I want to talk to you about a story that an experience I had when I was an undergraduate student a few years ago. So a few years ago. I was in third year organic chemistry, and the instructor at the time, who shall remain nameless, Peter Wan, was teaching the course, and he was becoming increasingly frustrated. Students were as well, because there was a group of students that were just like, could you slow down, could you slow down, you know, we got to draw this down, we need to draw this. And at one point in time, a couple of days into the course, so very early in the term, he was exasperated and turned around and said, don't you know how to draw the chair and boat conformers of cyclohexane? And half of the class, thankfully myself included, went, yeah, been there, done that all through second year organic. And the other half of the class was like, no, we don't know how to do it. How do you do it? That was a light bulb moment for a lot of people, the professor, myself included, because it started a discussion on why. Why didn't the students know how to draw any organic structure, as a matter of fact? And what it came down to as part of the discussion was that some of in second year there was two professors. One professor taught with a traditional whiteboard, chalkboard at the time, and he drew all the structures on the board and the students copied it down. Good. The other professor used this new technology called PowerPoint or something like that, and he had basically put everything into PowerPoint, so all the student had was a PowerPoint slides, and everything was just literally provided to them as PowerPoint slides. They didn't actually have to draw the structures. But when you actually had to do an exam, you had to draw structures on the exam. Students didn't know how to do this. They admitted that. And when they were in third year, it really became evident that their understanding of the material was hindered by their inability to try to visualize this in 3 dimensions and just simply to draw it as well. So all that comes down to the more work you do here, drawing structures, answering problems, thermodynamics, equilibria, whatever, the better it is for you. And for here, yeah, there's the questions are in the PowerPoint slides, but I'm going to be doing the majority of the work on the tablet, the modern blackboard, I guess is what you would call it. I would call it. So that's the story, and this is why you're going to be doing a lot of drawing and writing today. To give you an idea of where this all fits is that chemistry can be broken up into, well, historically 5 domains, now modern 2 domains, maybe 3. One of the domains is quantitative chemistry. Quantitative chemistry is physical chemistry and analytical. That's what historically they were. Physical chemistry looks at, the math, thermodynamics, electrochemistry, quantum chemistry, equilibria. That's all the realm of physical chemistry. Analytical chemistry is analysis. Going out and measuring soil, air, water, wine, whatever samples you happen to have, and coming up with numbers. What is the amount of this in there? What is the uncertainty in the calculations? That type of idea. Medical laboratory, determining, blood cell counts, chemicals in the blood, that type of idea. That's the quantitative side of chemistry. The synthetic side of chemistry is the design and synthesis of new molecules. So historically it was divided up into organic and inorganic. Organic really focusing on carbon-containing molecules, and inorganic chemistry focusing on everything else that wasn't biological in nature. What we realize in modern research labs is that what organic chemists use metals, and people who focus on the transition metals use organic ligands that bond to those metals. So the realm of synthetic chemistry kind of encompasses organic and inorganic. That being said, I'm not going to look at nomenclature involving metals. It is strictly going to be the traditional organic side of it. And once you get the nomenclature of the organic side of it, future courses can build what do we call it when we bond it to some sort of transition metal complex. There are going to be a number of simplifications that you're going to see as we go through today and Monday. Carbon and hydrogen are everywhere in organic chemistry. That's the backbone of biological organisms. So we simplify the structures by not explicitly labeling every carbon atom. We're going to find we're just going to be drawing lines, and wherever there is a vertex or a point, that's where there's a carbon atom. And because there's so many hydrogens floating around, we're not going to show any of the carbon atoms that are any of the hydrogens that are bonded to carbon atoms unless they affect the stereochemistry. Best thing about this is we're not going to look at stereochemistry in this course. Save that for an advanced organic course. Basically, carbon is known to form 4 bonds, and in organic chemistry it always forms 4 bonds. So if you see 2 bonds to carbon, the other 2 things that are not visible must be hydrogen atoms. And so we have these 3 different structures. And as a matter of fact, I realized as I was doing this earlier that I really should have put carbons right there as well to illustrate the fact that there are carbon atoms there all the way through this as well, to get a full 3D structure that represents all of the atoms that are present. We have a condensed structure. We have a 3D structure that's going to get unwieldy really quickly. And we have the line bond structure, which is what you're going to see if you continue on in organic chemistry. All of these 3 representations present the exact same information. So for example, in the line bond structure, this carbon atom that's right there, well, I'm going to just circle them. There's one there, there's one there. Okay, that carbon atom is bonded to, the one I kind of have the arrow drawn to, is got 2 bonds. So that means there are 2 additional bonds that we don't see and we don't represent, and those are the bonds to hydrogen. And it'll look a lot better once I draw it on the tablet. Okay, that would be the ones, of course, over here. How do we represent things in 3D? Well, we know that a tetrahedral geometry, which is the parent geometry when you have 4 things bonded to a central point, is tetrahedral. The bond angle is 109.47, 109.5 degrees. We need to be able to represent that 3-dimensional structure. And I'm going to stop right here and go over to a different program. There we are. Okay. This program is actually free. It's called Avogadro. And yes, it takes me a little bit to remember how to use it. This was completely on a whim last class. So there we go. That should work. Or not. Let's go with that one. There we go. Oop, that works well. There we go. Good. So here is a tetrahedral arrangement of atoms. This would be methane, effectively. And so I can arrange those hydrogen atoms such that there is one of them pointing straight up. That's the one at the top, and one pointing down to the right. And if that's that arrangement, then there's one coming out at you and one going back into the plane of the board. The way that we would represent that is the bonds that are in the plane of the page are represented with just a line. The bonds that are coming out of the page are represented with a solid wedge coming out of the page towards you. And the ones that are going into the plane of the page, change the text, are represented with a dashed line. And if you have partial bonds, you would have that as just a simple dashed line. This is a hatched line, sorry. Hatched line for the wedge going back into the page, and a partial bond is a dashed line. So what does this look like? So that representation of the carbon atom has a point right there. There was one going up and one going off to the right. There would be a solid wedge coming out of the plane of the page at you. Should probably draw this as just a line. a line that doesn't have a thing in it. There we go. So there's a wedge coming out of the plane, and there is a dashed wedge going backwards. Like that. So I'm trying to be artistic about it, and it's failing. To just redraw it, I would draw down and to the right. There's a wedge, and there is a hatched wedge going to the back. And I never get my hatched wedge to get bigger as I go back, whatever. That's the representation. There are two options with regards to that wedge. The point of the wedge can either indicate the point furthest away from the reader, or it can indicate the location of the carbon atom. And that second one, where the point on the wedge indicates the carbon atom, is becoming more commonly adopted and accepted. So that's what we're going to present here and use in this course. All right, well that takes us to actually doing examples. And before I do examples, I'm just going to go back over to here. And just want to point out one thing, that in terms of arranging this, if I were to make the two atoms in the plane of the page form an upwards V, as they do right here, then coming out the bottom is one coming at you and one going back into the plane of the page. If I move this thing over just a tiny bit, oop, that's bad. That's not what I want to do. Like I said, haven't used this for a while. I can also reverse that and have the V going downwards, so the ones that are in the plane of the page are going down, and if that's the case, then coming out the top, one's coming towards you, one's going back. We're going to see that when we do the 3D structures here. So, let's back up to there. These are the entities that we're going to be looking at right here, and it's just a matter of sitting down there and going through and actually doing them. So the first one we have is, just to redraw it, make this reasonable size, CH3, CH2, CH2, that complex right there. Knowing that carbon forms 4 atoms, what we're going to do is we're going to break it up into the carbon atoms that form the backbone. Anything that's in brackets is not part of the backbone. It's attached to a carbon atom that is part of the backbone. So there's a carbon atom attached to different things. So I've just isolated all of the carbon atoms that form the backbone, and there are 1, 2, 3, 4, 5, 6, 7 of them. Okay? Now what we're going to do is we're just going to literally write them out separately to get an idea. If we have a CH3 group, that's 3 hydrogens bonded to a carbon. It can only form 1 bond. A CH2 group needs 2 bonds, and this one right here is not a carbon bonded to hydrogen, but it's a carbon bonded to CH3 groups, 2 of them, so it actually still needs 2 bonds in the backbone. There's another CH2 group. There is a CHBr, in the sense that it's now a carbon bonded to a hydrogen and a bromine, and of course bromine also only forms 1 bond, so you're still left with 2 bonds needing to be formed, and at the very end you have a CH3 group as well. The way we arrange the backbone, or the main chain, which was those 7 atoms, is we put it into a zigzag configuration. This gives bonds that are in the plane of the page. So there is that representation of those 2 bonds in the plane of the page in a downwards V. And then we can just keep doing this, and it's in an upwards V here. So we are arranging the carbon atoms such that 2 of the bonds are always in the plane of the page. And I need 7 of these. 1, 2, 3, 4, 5, 6, 7. All right. Now, it doesn't matter if I start down or up. I could easily have done this and had it represented like that. It doesn't make any difference. However you feel comfortable doing, I'm just going to go back to what I had originally, like that. That is the backbone. That represents all of the bonds that are formed here. And so on and so forth. Okay? Is what's presented there. All of those bonds are there. Now we just need to put on all of the other atoms. And all of those other atoms would be, in the case of the first carbon atom, another 3 hydrogens. And I'm just going to do it slightly in a different color, just for fun of it. There still can be 1 in the plane of the page. And then what would happen is that there'd be 1 coming out towards you and 1 going back into the plane. For the one that's up at the top, I have a downwards V, but that means on the opposite side there's 1 coming out of the plane towards you and 1 going away from you. Similarly down here, same thing. Like that. So that's the first 3 carbon atoms. Then it becomes 2 CH3 groups. And this gets a little messy. So 1 is going to go to H3C, CH3. Try to make it like that. If I were to draw those things out in, what do you mean by the plane of the page? The line, literally the paper that you see, sorry. Taylor, if it's still confusing, let me know. But literally, as presented here, whenever it comes back, it is literally on the paper. That's where the bond will be. I'm going to give you another structure in a few minutes. Once I get this one done, we'll go back to the Avogadro, and I'll show it for a simpler molecule. So that's the 2 CH3 groups right there. Then it was a CH2. Then it was a hydrogen and a bromine. Okay? And finally, this one can sit in the plane of the page. And we get the CH3 group at the end. And to be honest, this isn't actually even the full 3D structure because we still have these 2 CH3 groups that we haven't expanded fully. Okay, to try to visualize this, I'm going to go back to this program and I'm going to create propane. I have to get an optimized structure here, and now I've got myself an optimized structure. Good. So this is the arrangement of propane, and what I want to remember how to get to draw this thing. There we have it such that it is in a downwards V geometry. We go up and then down. And if I were to turn this thing 90 degrees, you can see that everything lines up. That's what I mean by the plane of the page. The hydrogen, the 3 carbon atoms, and even the hydrogen at the very end is all lined up in the plane of the page. Let me see if I can remember how to move things around. Nope. Nope. We'll work on it. Ah, this one. Nope. All right, we'll work on that right now. Just there we go. That'll work. So there it is in terms of the arrangement in the plane of the page. And what we've got, you can see with the downwards V here, coming out the bottom is one going towards the back, one coming towards the front. And up here, one's coming out of the plane towards you, one's going backwards away from you. That's the arrangement of the atoms that I am trying to illustrate when I draw them on paper. Again, there they are, nicely perfectly in plane. But when I turn it to make those two bonds in the plane of the paper, I end up with, as you see right there, things coming out at you, things going away from you. All right. Taylor, does that answer your question? What we need to do now is draw the, that's the 3D structure, and we're not going to expand the CH3 groups at the top, although on the worksheet, some of them asked you to do that. Let's look at the line bond structure just so we get all of it together. The line bond structure has the backbone just as vertices, so that the backbone that's right there just exists as points, like that. And off of this one carbon atom, there is two CH3 groups, and off of this last one, we'll just make it go back, is a bromine. So everywhere there is a point or a vertex is where you have a carbon atom. And there's 7 in the backbone and 2 coming out, 2 methyl groups coming off of there. And you're not quite correct on the structure there, David. We'll get to that though. That's actually probably going to be next day. I need to ask the class in the chat, for how many of you is this brand new, so new, and how many is it a review? So I would say that more than half of the students are saying it's new, and the rest are saying it is a review. So with regard to the structure, David, yours was very close, and we'll see. We're going to come back and we're going to name it in a little bit. Someone else mentioned what happened to the hydrogens on the end, and the hydrogens aren't drawn in the line bond structure. So we know, I'm just going to have to erase my little circles here. Oops. Trying not to erase too many bonds. We know that because there's only one line there, there's going to be 3 bonds to different hydrogens. But those are not represented in the line bond structure. Okay? Good deal. So that is what, just to finish that off, I forgot the methyl group right there. Right there. Good deal. So that's the first one. Let's look at the next one. The next one is, and I'm going to do it, if you, this is a review for you, it's going to go a little bit slow. We're going to pick up speed in a little bit. Oh, and there's an error in your notes. It is not CH, it is just simply COH, CH3. Get rid of that hydrogen that is erroneously there. There we go. So to break it up into its constituents, apparently I left breaks. Those are the carbon atoms of the backbone, 1, 2, 3, 4, 5, and 6. Anything that is in brackets is not part of the backbone. It's attached to a carbon atom that is part of the backbone. So that OH group and that CH3 group are attached to, of course, the carbon atom number 3. So the backbone is those 6 carbon atoms that we're going to draw in a zigzag fashion. 2, 4, 6. And then we're going to try to put on these, the hydrogens are fairly easy. We've got this functional group. That is a carboxylic acid group. And if you remember from Chem 101, a carboxylic acid is a double bond O to OH. This is trigonal planar because of the geometry. So it can actually sit in the plane of the paper, like that. There's your trigonal planar geometry. When I add in the, actually I could probably, just let me redraw it in a different color, double bond O, HO. Then we have the hydrogens, and following the same pattern, this one is not hydrogens, but it is, oops, not that, that. And here, if I was going to be particular about it, and I am going to be particular about it, that's an O bonded to an H, and here we can have that same arrangement where you have the carbon atom with 1 in the plane of the paper, or 2 in the plane of the paper, 1 coming out towards you, 1 going back at you. That is the methyl group drawn out in full. And again, on the end, 1 can still be in the plane because it would just be the continuation of the backbone. And the other 2 would be like that. So the question is, do I always want you to draw it in full? And yes, on the worksheet, only the simpler molecules are going to have, I'm going to expect you to draw out in full 3D. And full 3D would involve things like drawing out all of the functional groups in their entirety, showing all of the bonds. Yes. The last thing we want to do here is draw now the line bond structure. Get rid of that. And again, that backbone is simply replaced by a zigzag line. Off of the first carbon atom is the carboxylic acid group. And off of the third carbon atom, still in 3D, we have we don't need to draw the CH3 because that's representative, but we do need to say that there's an OH group right there. And so all 3 of those things present the exact same information. And my goal is for you to be confident by the end of completing the worksheet that you can read that and realize what it is in 3D and what the bond structure is like that. It will become impossible very quickly to draw the full 3D and even to write out the condensed formula for some very complicated organic molecules. And you will be exclusively using the line bond structure that's presented down below. Go ahead, Efren.
So in your line bond structure, what is the reason that you don't draw the CH3 in the middle part?
Oh, because it is represented. So if I were to get rid of that and that and that, you can see, well, if it was drawn well, that there is a dashed line going down there. It's going off into space. So the carbon atoms exist wherever there's a vertex and wherever there is a point. There is a point at the end of that bond right there, and there is a point down there. And so that is where you're going to find the carbon atoms. Okay, Efren?
Oh, so you draw like those lines, but you don't need to put your carbon.
You don't need to put a CH3 group there, no, because that's inferred from the fact that the point goes into space and stops. There has to be something at the end of it, and if it doesn't tell you explicitly what it is, it's a carbon atom.
Okay.
Good. All right. Are there any other questions on this? Not that small. Ooh. Sorry, the screen decided to go places. Are there any other questions on this? Don't worry, we'll get back to naming these things next day. Want to do the next one? The next one starts off with cis and then then a chemical structure, whatever cis means. All right. This explicitly, cis, it refers to the double bond. And this structure is nice because it actually tells you the double bond's there. I could equally have said CH. These two are the same. And as you get more comfortable with it, you start to look at this and you go, wait a minute, there has to be a double bond there because there's not enough hydrogens bonded to the carbon. So the top one explicitly tells you there's a double bond. The second one, it's implicit. And with your knowledge of chemistry, you can figure out that there's a double bond there. The concept of cis and trans represent how you arrange the atoms around that double bond. So if you have cis, you mean they're on the same side. And the other one is trans, you're going to see they're on opposite sides. And this refers to the carbon atoms, not the hydrogens. Yeah, we'll just leave it at that for now. It gets more complicated as you get more complex structures. So cis and trans are for the simplest form of double bonds. So, and we're dealing with things that are cis. So in terms of drawing this, I'm going to go down just a little bit, and I'm going to put my double bond like that. And if things are on the same side, that means my two bonds coming off of it do that. These two are on the same side, and they're going to go to other carbon atoms. And then I'm just going to finish off how many carbon atoms were in my backbone. That's kind of something I need. 1, 2, 3, 4, 5, 6 carbon atoms in my backbone. So in my representation, 1, 2, 3, 4, 5, I'm going to need 6 carbon atoms there. And now it's just a matter of putting in all the substituents. Conveniently, just going to change color. These happen to be 2 hydrogens. If they aren't hydrogens, we can't use cis and trans. It only works if there's 2 hydrogens, 1 on each side. So advanced organic courses are going to deal with what if there's more carbons coming off of that double bond. But for us, cis and trans work just fine. H. I believe that was what was there. Oh no, this last one is not hydrogen, it's a CH3 group. Carbon, hydrogen, hydrogen, and another bond off that way. As best as I can represent bonds in the plane of the page and coming in and out. And then after that, it was CH2, And this one was CH2OH, so oxygen bonded to hydrogen, and I just find it convenient. That would be the representation of the full 3D structure of that complex. To draw the line bond version of that, we're going to start with double bonds, like that. So that represents the backbone. There's a double bond there, and then we need to realize that there is a carbon coming off of there, and an OH group coming off of there. So those two representations are the full 3D and the line bond structure of this complex. Does anyone have any questions? Okay, what's going to happen is if we go back and look at the notes, what we've done is we've done our, so Taylor's question, are on the CH3, are there two hydrogens on the same page? Yes, there can be. There can be two hydrogens on the plane of the paper. You can always arrange it. If I were to go back over to here, you can always arrange it, no matter what you do, to get two hydrogens, and I can't make, oh, there it goes. To make two hydrogens, no matter what you do, you can always put two hydrogens in the plane of the paper. And it's, yeah, completely possible to do that. So we just do that. It just makes it easier for drawing. I'm sorry, I just got to go back and find your question. There it is. What would it look like if it were a trans molecule? We'll see an example of that next day. We'll do that. So let me just go back and talk about what we're going to be doing next day. Is we're going to continue this page. We're going to look at those bottom ones down below. Those are line bond structures and convert them back to condensed structures. We're going to look at, well, hydrocarbon nomenclature. Going to continue. Look at a bunch of functional groups. And here we have the functional groups as presented. And so figure out this is just a list of some common functional groups. And look at the rules for nomenclature, and then go back and start naming things. So drawing them and naming them, putting it all together. And we're not going to get through all of these examples. We don't have enough time on Monday to do that. They're just representative. I will pick and choose which ones I want to do. The worksheet is just the application of these rules to different structures. And so I'm just going to pick ones that show different things, and hopefully we'll get it all, there's a good portion of it done on Monday. All right. That concludes what our time for today. So all the best. If you have any questions, I'll hang on here and can answer your questions. So William, since you're still here, you asked what it would look like if it was a trans molecule. I'll just draw it out for you. You would have, there's your trans structure. And
hey, Roy,
yep.
I'm not sure we're supposed to be seeing it on the screen right now.
Oh, whatever. 3. My apologies. Good call. Thank you.
All right, thanks.
There's your trans structure. Yes, William.
Okay.
So now, in terms of the trans structure, the two carbon atoms are on opposite sides of that double bond.
Okay, that makes sense.
And David, yes, that is correct. Except bromo isn't capitalized. 2-bromo, 4,4-dimethylheptane. That's correct. When are you going to get your exam marks, Haley? Hopefully this weekend. the exams, I've asked the TAs to have the exams marked by Sunday, so hopefully we'll get everything up and online by then, okay? Go ahead, Taylor.
I just had a question. Can you scroll back up to the last 3D we did?
There you go.
So for on the CH3, you have two hydrogens on the same plane, but then on one beside it, how come the hydrogens are on different planes?
Which one are we talking about?
Like any of them, like, because all of the carbons that are just like CH2, all of the hydrogens are either going like, I think it's out of the page to like.
So I just circled two right there.
Then on the CH.
Yeah? But,
Yeah.
oh, you're talking about on the
same
CH3
plane.
on the group over here?
No, on the one that comes off of the.
Oh.
See where it's like the.
This one up here?
The one in the middle. Yeah.
Yeah, okay.
That one.
So it's drawn, I'm not going to say it's drawn well, but the reason why I represented it like that is because I can take anything and, okay, I'm going to just mess around with this structure just a tiny bit. Let me just delete a few things that are here. So if I wanted to, let me just see what I want to get rid of. There we go. So put a hydrogen there and put a hydrogen there. So it is by convention that we put the carbon atoms on the backbone, but there's nothing stopping me from doing that. So the one that came out of the page, or I guess this case it went back into the plane of the page that we have presented here, it's already got a bond basically coming towards it. So I can, with this representation, I have 3 bonds to put. I can make one go upwards, one go in the plane, and one go wedge. I can always get 2 of them to sit in the plane of the page. It happens to be that the bond to carbon is going back into the page towards it, okay? So that means because of that, I have the ability to put still 2 bonds in the plane, and I just make them both hydrogen. It's just convenient to make them both hydrogens. Does that answer your question, Taylor?
Kind of. But so how come you can have both hydrogens on the same plane there, but then like on the one below it, where you have 2 hydrogens, how come those ones can't be in the same plane?
Okay, the one down below it, let me just get back to this. So if I wanted to, for this down below, so let me just, again, delete a few things to make life easier. There we go. I could have, I'm just going to get rid of this, the entire CH3 group. I could have, for this one that's down below, had made this a hydrogen and made this go to the CH3 group. That would work too. It's just by convention, I want to draw everything as on the plane. It just makes it easier to go that way. And the reason why this one is not part of the backbone, or the reason why it's not on the plane of the paper, is because it is not part of the backbone. So in this one that I just drew down here, I've got 2 carbon atoms. Oh, so I guess they're not 2 hydrogen. I put a hydrogen in the plane, but I made the carbon go backwards just because I was deciding to be silly and drawing a really bad structure.
Oh, okay, I see.
So if I go over, hold on a second, that should be Control 2, and I make my propane again, just quickly get a stable structure here. So with this arrangement here, I have conventionally put the carbon backbone on the plane, but there's nothing stopping me from putting, right now in this arrangement right here, there is the bond to the carbon on the left and the bond to the hydrogen on the right. Those are in the plane. It just makes that CH3 group going to the back, inconvenient to see. Does that make sense?
Yeah.
And
That makes sense now.
And,
Thank you.
no, hold on a second. I just realized I can actually do it here too. You are seeing this, yes you are. Okay, good. What I've just done is I've literally just made that section of the functional group that I was trying to represent. So there now, the backbone is still there, and I could continue drawing the backbone if I wanted to. So there's the backbone continuing, but we have this carbon atom in that central point that's at the back, and the reason it's pointing to the back is because it takes the place of one of the hydrogen atoms. And if I wanted to go and look at, oh, wrong one. It's not the most intuitive software, honestly. I can arrange it such that with the thing going to the back, now these two hydrogens, I can't draw, unfortunately, on this program, but the two hydrogens that are at the very top, can you see the mouse pointers? Taylor?
Yes.
You can see the mouse?
Yeah.
Okay, the mouse is pointing to two hydrogen atoms. They're in the plane of the paper. And what you have is one bond coming towards the central backbone and one going further back. Okay?
Okay. Yeah. No, it makes more sense to see it.
Yeah, I understand. All right, sounds good.
Okay. Thank you so much.
That answers your questions?
Yes, it does.
Excellent. Okay, we'll just go to there, and that way everything's good. All right, sounds good. Anyone else have any questions?
Yes,
Rufaro.
hi Roy.
Yep.
On that same question, on carbon number 4, does it matter whether I put the CH3 coming out of the page first and then I put the hydrogen going into the page? Or there's
For our
Consider what I'm-
for our purposes, I'm thinking you're talking. Let me just delete a few things. You're talking about this down here, or sorry,
I'm talking about
the one up top, right?
One with the CH3 and H.
Yeah,
Yes, that one.
that one. Okay. So for our purposes, it doesn't matter.
It doesn't matter.
It doesn't matter. However, when you get to an advanced organic chemistry course, what you're going to find is that it's actually, given the structure, it's actually two different compounds. The one which it comes out towards you is actually a different compound than the one that's going farther to the back. Okay, that you actually are forming what are called enantiomers. And I'm not going to talk about enantiomers in Chem 101, but yes, for our purposes, it doesn't matter. In advanced chemistry courses, you'll realize that you're forming enantiomers.
Okay, thank you.
Okay? But I'm not going to mark you on enantiomers or anything like that. So, like I said, for our purposes, no big deal.
Okay,
Good.
thank you.
Not a problem, Rafaro. Take care. Does anyone else have any questions?
Roy, I just have a quick question not related to this. I just want to know, did you get my email about just
Yes, I did.
volunteering to?
Yep.
Okay, cool.
I did get it.
Is that cool?
Yeah, that's fine. I'm not responding to, I probably got about 50 emails, and it was just, yeah, I wasn't responding for changes. When you get the next schedule, the revision will be there and you'll be able to see. I didn't think it was
Okay.
enough to, it wasn't a major change or anything like that, so I just said, yeah, sure, I'll move you there, and when you see the next schedule, you'll have moved to the front.
Okay, awesome. Thank you. I know sometimes profs lose like emails because they get so many, so I just wanted to make sure you got mine.
No, not a problem. Thanks a lot for checking in with me, Afrin. Good deal. Anyone else have any questions? What would be the name of the last structure? The one that I completely destroyed? Hold on a second. I need to go to there. Are you still there, David? Yes, you are. Okay. So the last one we drew, if this comes back, there we go. 1, 2, 3, that's 6, that's hexane. The alcohol is going to be dominant. So you're dealing with 1, 2, 3, 3 methyl, 1, 1, 2, 3, 4. Yeah, cis 3-methyl, hex 4-ene 1-ol. I'll draw that out for you. That thing is cis 3-methyl hex 4-ene 1-ol. We're actually going to go do that next day, but yes. Good deal. Are there any other questions from anybody? All right, well, everyone have a great day. I'm going to stop the recordings.